Yes, so hello everybody. Again, we are here with another video, with another lesson. Of course, in grade 10, grade 10's book, well, lesson 3. We're going to talk about something that you already studied again in grade 7. I mean, the concept, the idea of it. Then in grade 9, you study something like else about it in advance. And today, in this lesson, you will study it in more detail, with more detail, and you will study something else regarding to it that is directly related to the grade 12. All right? So the title is Absolute Value, and today we're going to talk about absolute value and its characteristics. Okay? So regarding to absolute value, we have got like different ideas. When we have absolute value of just number, let's say numerical examples, and when we have algebraic expression inside an absolute value, what is going to happen and how are we going to find the result? How are we going to deal with it? Perfect. So in the first slide, we are going to deal with some numerical example regarding to absolute value. So you better know that whenever we have number in an absolute value, no matter it is negative or positive, the result is always going to be positive. So let's just try it, the thing that we said practically. Okay, absolute value of 4. So we have got 4 as a positive inside the absolute value. So the result is going to be the same. Let me just bring my pen. Perfect. And pretty sure the size is not that much. Okay, perfect. So since it's positive, so it's equal to the same thing, which is 4, because we are saying that absolute value of 4 is equal to 4. 4 must be positive. Even if there was absolute value of negative 4, the result was again 4, because I'm telling you the function, the job of absolute value is making everything positive. Perfect. How about here in the next one? We have got a BEDMAS problem, orders of operation. So we have 4 minus 17, okay? 4 minus 17, well, the result here is 4 minus 17, it's equal to negative 13. Since we have absolute value around it, so the result is going to be positive 13. Because I'm telling you, whatever comes out as an output, as an outcome from the absolute value, it's going to be with positive. Perfect. How about this one? Negative 2 minus 8. Well, negative 2 minus 8. Remember the result of these two when we add two negative numbers. We will add them, but still keep the negative sign. Okay? So the result is negative 10. And we have absolute value around it. So it's going to give us positive 10. And I hope that it is clear till now. How about absolute value of negative 1? So absolute value of negative 1 is just positive 1. All right? Absolute value of negative 1 over 2, it's equal to 1 over 2. Of course, positive. Okay? Because that absolute value will make everything inside, will make the result positive. How about here, absolute value of 0 minus 7? Well, absolute value of 0 minus 7, it's equal to negative 7. So absolute value of negative 7, it's equal to positive 7. That is regarding to absolute value of numerical problems. Perfect. So let's move to the next slide, which is the most important thing that I want you to learn it in this lesson perfectly. How are we going to redefine an absolute value function? Which, what I mean by redefine, rewrite it without the absolute value symbol. For example, here, as a note, we have it to redefine an absolute value function. Writing without the absolute value notation, symbols. We have got 2 steps. First, we will equalize inside the absolute value to 0. Whatever we have in terms of algebraic expression, of course you are going to deal with an algebraic expression, for example, a linear equation. Whatever we have inside the absolute value, equalize it to 0. And then find out the value of that variable that you have it. That's going to be called a boundary point. So we will equalize inside the absolute value to 0 to find the point of boundary. This is boundaries, or it should be boundary. The point of boundary, or we can say to find the boundaries points. For all the values greater than the boundary point, the function will be positive. And of course, for the values smaller than or less than the boundary point, the function will be negative. Let's just do it numerically. Imagine, before going to the next slide, because I'm pretty sure there will be some examples. So I would just give you one example here and solve it by following these two steps. Let's say if we have absolute value of 4x plus 20. And the question is, redefine the function absolute value of 4x plus 20. So the first step, as you can see, it says that equalize inside the absolute value to 0. What do we have inside the absolute value? 4x plus 20. Equalize it to 0. Why? Because our target is to find the point of boundary, so which means we should find the value of x. So how are we going to deal with this equation? You already studied it. Like, if you move this 20 to the number side, so it's going to become, here is positive, it's going to become negative 20. So we will have 4x equals to negative 20 divided by 4 divided by 4. Then x would be negative 20 divided by 4, negative 5. That is the point of boundary. So based on that point, we are going to redefine our function. How? You will find it out, you will come and say that, okay, our function, which is absolute value of 4x plus 20, is equals to, that notation, I hope that you can learn it, equals to 400, it says that in the second steps, for all the values greater than the boundary point, for all the values greater than or equal to, okay, I forgot to write equal to the boundary point, which is negative 5, the function would be positive. So it means no change. Nothing will happen to the function. 4x plus 20. For all the values greater than negative 5, that function would give us a positive number, a positive outcome. For all the values smaller than the boundary point, the function would be negative. Negative 4x plus 20. You might ask me, teacher, can we multiply that negative by whatever we have inside? Yes, you can. Negative 4x minus 20. Both of them are correct. But I suggest you to write it in this way. So this is exactly how you are going to redefine that function without the absolute value. Okay? By using boundary point. So in order to check our job is correct or not, let's take some points. It says for x greater than negative 5. Tell me an x greater than negative 5. Excellent. So negative 4, negative 3, negative 2, negative 1, 0, 1, 2, any number. So let's say 0. 0 is greater than negative 5. So 4 times 0, of course 0. Plus 20, positive 20. So the result is positive. You see, for values greater than negative 5, you got a positive result. How about for values less than negative 5? Let's say negative 6. So 4 times negative 6, negative 24. Negative 24 plus 20, you're going to get negative 4, which is a negative amount, a negative number. So it's going to tell us for all the values greater than negative 5, we will have a positive result. For values smaller than negative 5, we are going to have negative results. That's all about redefining a function. So let's go to the upcoming slides and see what kind of example do we have. Yes, without using the absolute value symbol, redefine the absolute value of 2x minus 4. How are we going to redefine this one? As we said, first of all, look what we have inside our absolute value. What do we have here? We have got 2x minus 4. So equalize it to 0. Equals to 0. Move this negative 4 to the other side. So 2x equals to 4 divided by 2x, sorry. 2x divided by 2 divided by 2. Why do we divide? Because the inverse operation of multiplication is division. To remove these two, we need to divide it by 2, both sides. That 2 will kill these 2, and x equals to 2. That is the boundary point. Based on this one, we will redefine our function. You are going to say that, okay, absolute value of 2x minus 4 equals to, for all the values greater than 2, for all the values greater than or equal to 2, the function would be positive, 2x minus 4, no change. For all the values less than 2, the function would be negative. So a negative would be added to behind the function 2x minus 4. You may just multiply this negative by each term inside the parenthesis and write it in this way: negative 2x plus 4. Y plus negative times negative, positive. So if you want to say, you might tell me, teacher, so what else? This is the solution, by the way. This is what we mean by redefining the function. From absolute value, it became a function without the absolute value notation, but of course with some conditions. Okay, for all the values of greater than 2, we will have positive result. For values less than 2, we will have negative result. That is regarding to redefining the functions. Okay, so let's move to the next slide and see what we have. So the next slide is again a question. Without using the absolute value symbol, redefine the absolute value x minus 3. So let's just do it. What do we have inside our absolute value? Perfect, x minus 3. So make this x minus 3 equals to 0. Then move this negative 3 to the other side, and the value of x, which is our boundary point, is going to be 3, which is boundary point. So then you are going to say that our function x minus 3 equals to, for all the values greater than or equal to 3, our function would be positive, so no change would happen to it. X minus 3. For all the values less than 3, the function would be negative. X minus 3, a negative behind it. Again, you may just multiply that negative by each term inside, so it's going to become negative x plus 3. Okay? This is how we are going to redefine a function. And I hope that it is understandable till now. So let's see what we have next. We have got 2 examples here. I want you to just stop the video and try yourself, test yourself, whether you got it or not. Solve these 2 questions. In case if you stuck in them, try to share your problem, your question in the comment. Okay, take a photo or stop. Perfect. So the next thing that we are going to deal with it in this section is regarding to the solution of an absolute value equation. So note, when an equation has no solution in real numbers, it's represented as an empty set. It's represented as an empty set denoted by that symbol or this one. When an equation doesn't have a solution, we are going to say that the solution set is empty, and we are going to donate it, show it with these 2 notation. Either that one, it just looks like a 0 and a line that intersected, or a Q, or these 2 kind of brackets. Okay, there is nothing inside, so it shows an empty set. So let's see what we have here. Okay, f of x is a linear function. Remember, if it is a linear function, next, fa is a positive number. The equation of absolute value of f of x. Remember, we said f of x is a linear function, so it is a function inside this absolute value, equals to a. A is positive. It has 2 different values, one positive, one negative. Just like the thing that you already studied. Imagine if we have if we have absolute value of x equals to 9, our linear function is x, our a is positive 9. So the answer, the solution set, the set of the solutions can be like both positive 9 and negative 9. Why? Because absolute value of positive 9 equals to 9. Absolute value of negative 9, it's equals to 9. So these are the possibilities that x can become. Alright? Therefore, you are going to say that the solution set is positive 9 and negative 9 both. So the next thing that we have, we will talk about it in upcoming, like in next slide, of course, with different examples. So the next situation is if a is 0. In the first one we said if a is positive, so the function is going to have two different values, two different solutions, one positive, one with negative. What if the result is equal to 0? How many solutions are going to have? So the equation f of absolute value of f of x equals to a has got only one value, one solution, which is we are going to equalize the inside the root, inside the absolute value to 0. Example. Let's say if absolute value of x minus 1 equals to 0, so it has only one solution, which is take out the inside the absolute value x minus 1 equals to 0. Why 0? Because the absolute value, the function, the equation itself equals to 0. Alright? So it says if a is 0, that equation is going to have only one solution. So move this negative 1 to the other side, it's going to become positive 1. So x equals to positive 1. This is the only solution that this kind of equation is going to have. Alright? And the next situation is, what if a was negative? What if a was negative? If a is a negative number, then the equation of absolute value of f of x equals to a has no solution in real number, and the solution set is going to be empty. So we are going to donate it with this one. Example. So imagine if absolute value of x minus 15 equals to negative 1. We are always saying that absolute values, the answer of absolute value is positive. Since it says the answer of this absolute value is equal to a negative, so we will say that there is no solution set for this one. There is no solution. Therefore, the set or the solution set is going to be empty. There is no solution for this one. The solution set would be empty. So solution set is empty. That's it. Okay, for this one, the solution set was only 1. For that one was positive and negative 9. So let's see what we have next. So regarding to that matter, that f of x was a linear function in an absolute value, and if we had an equation, so the other side of the equation was a positive number or 0 or negative, there will be different situation, and I want you to take care of them perfectly. So we have example. Solve that equation and evaluate the solution. So at the end, we need to evaluate whether the solution is correct or not. So let's just do this question. Absolute value of 2x plus 3 equals to a positive number. So since it's equal to a positive number, it has got two solutions, either with positive 1 or negative 1. So we are going to solve it like this. Bring this out, 2x plus 3. Either it's equal to positive 1 or it's equal to negative 1. So let's go with the positive one first. We're gonna say that 2x plus 3 equals to 1. Move these 3 to the other side. So we are gonna have negative 3. 2x equals to 1 minus 3, it's equal to negative 2. Try it. Move these 3 to the other side, it's going to become negative 3. Divided by 2, divided by 2. These 2 will cancel these 2, and x equals to negative 1. Clear? Perfect. How about if we go with the negative 1? So 2x plus 3 equals to negative 1. So again, move these 3 to the other side. So it's going to become negative 3. So 2x equals to negative 1 minus 3 is equal to negative 4. 2 negative, when you add them, it's equal to 4. You will add them, but still keep the negative sign. Okay, divided by 2, divided by 2. That 2 cancel these 2, and x equals to negative 2. Negative 4 divided by 2, it's equal to negative 2. Right now we got 2 solutions, as we expected, because the absolute value, if it is equal to a positive result, so we are going to have 2 solutions. So we are going to evaluate whether our solutions are correct or not by substituting them into the absolute value. All right, 2x, 2 multiplied by negative 1, negative 2. 2 multiplied by negative 1, negative 2. Plus 3, well, inside the absolute value, it should be equal to 1. Is it? Let's just try it. 2 times negative 1, negative 2. Plus 3, it's equal to 1. So exactly 1. Therefore, this one is a solution. It's included in the solution set. How about negative 2? Well, 2 times negative 2, 2 times negative 2. Plus 3. 2 times negative 2, negative 4. Plus 3, it's equal to negative 1. Absolute value of negative 1, again, it's equal to 1. Since it's equal to 1, so we are going to say that the solution set is both negative 1 and negative 2. Negative 1 and negative 2. That is how you are going to solve such a questions, evaluate it, and write the solution set. And I hope that this is clear to you, ladies and gentlemen. So let's move to the next slide. Yes, we have got the second case. An absolute value equals to 0. Perfect. Let's choose black. It's more clear. So inside the absolute value 3x plus 6, that rule as if our f of x, which is our function, equals to, we set if our equations equals to 0, so we are going to have only one solution, which is equalize it to 0. So move these 6 to the other side, so we are going to have 3x equals to, here 6 is positive. When it goes to the other side, it's going to become negative 6 divided by 3 divided by 3. So 3 will kill 3. X equals to negative 6 divided by 3, negative 2. That is the solution that we got. Only one single solution. Let's just evaluate it. So instead of x, put negative 2. 3 times negative 2. 3 times negative 2 plus 6. Is it equals to 0 or not? 3 times negative 2, negative 6. Plus 6. Inverse operation, so the result is 0. So that means that our solution set equals to only negative 2. This is how we are going to deal with this type of questions. Okay, the next one, the next question, the next slide, let's see whether we have it or not. Perfect. Very nice question. It's, oops. Okay. So 11 plus absolute value of x minus 2. 11 plus absolute value of x minus 2 equals to 0. First of all, we need to move this number to the number side. It's positive 11. When it goes to the other side, it's going to become absolute value of x minus 2 equals to, it's positive, so it's going to become negative 11. Remember, in the third case, we said that if absolute value equals to a negative number, there is no solution for that equation. Okay? Since the absolute value is equal to negative, so the solution set is empty, or you can just donate it in this way. Okay, there is no solution. There is no number that if you put it here, the result would be equal to negative 11. You might say that, teacher, we can put 13. Tamam. 13 minus 2 it's equal to 11, not negative 11. You might say that, okay, negative 7, negative 9. Tamam, negative 9, negative 2, it's equal to negative 11. But since there is absolute value, so it must be positive 11. Therefore, whenever an absolute value equation equals to a negative amount, there is no solution for the solution set. Perfect. Let's move to the next station of this lesson, graphing absolute value, which is one of the most important topic in grade 12, not only in grade 10. Okay, so grade 10 must be like grateful that the Ministry of Education, they added this stuff to their new book, okay? Because from now, you will get prepared to deal with the questions regarding to absolute value. Okay, instruction says that to graph absolute value, how are we going to graph an absolute value function? We have got, by the way, I want you to know that y equal to absolute value of x, we call it parent function of absolute value. Okay, parent function of absolute value function is y equal to absolute value of x. It's the simplest form of absolute value of x. Okay. To graph absolute value function, equalize inside the absolute value to 0. After finding the value of x, then take two inputs smaller and 2 points bigger, and then find their y values. So as you can see here, there is an absolute value function, which is the parent function, and a table. So imagine if our function is absolute value of x. Make inside 0, x equals to 0. Take 2 points smaller, 2 points bigger. So 2 points smaller are negative 1 and negative 2. 2 points bigger are 1 and 2. Okay, so let's just find out their y values. Okay, which is f of x. Okay, so absolute value of 0, it's 0. Absolute value of 1, it's 1. Absolute value of 2, it's 2. How about absolute value of negative 1? Absolute value of negative 1, it's equal to 1. Absolute value of negative 2, it's equal to positive 2. Okay, what was the job of absolute value? Make it, everything make the result positive. Perfect. There are two important notes regarding to absolute value function that you must know them. Okay, as you know your names. Domain and range. These are the two words that you will deal with them in grade 12, especially a lot for different type of functions. But here is one of them, which is absolute value function. So domain of absolute value function is all the real numbers we can use to graph a function, which is on x-axis. By the way, we will measure, sorry, I'm going to come back. So the video has no problem. Okay. We will measure the domain of a function according to the x-axis. Okay, what values the function can get as an input. As you can see the graph, based on the graph, clearly we can decide. On x-axis, we can take every single value that we have it on real number. Yani everything can go inside the function. Therefore, we are going to claim that domain of absolute value function is all the real number, which is R. All the real number. So domain of absolute value function is all the real numbers. What I mean by that, for example, you can put 2, you can put negative 2, negative 1 over 2, negative square root of 2, everything. So it has no problem. That's why domain of absolute value function is R, which is all the real numbers. How about the range? So range, the set of all real numbers we get as output. That is the definition of range. Okay? The set of all the real number that we can get as an output in our function. So we are going to count a range on y-axis, because y-axis shows the set of the outcomes. Okay, so based on the y-axis, we will decide about the range. How about the range of absolute value of function? So we said that domain of absolute value function is R. Domain is all the real number for absolute value function. How about the range? Well, as you can see, the range of our graph, look, the graph starts from 0. Okay, we don't have any negative number. That's why negative number are not included in the range of the absolute value function. We started from 0, look, from the lower part, from the lowest point to the greatest point. So the lowest point is 0. So range is from 0 to, so it goes up. Okay, there is no bound, by the way, for this absolute value function. Therefore, you are going to say that it's boundless. So it's from 0, closed interval, until positive infinity, open interval. But according to some book, they show it in this way. Both of them are okay, but in your book, open interval show in that way. So the domain of our absolute value function is all the real numbers. And for the range, it's from 0 to positive infinity. That is for the range of a parent function of absolute value. So if we add the numbers, subtract, so multiply, of course it's going to change. So let's see the questions that we are going to deal with them. So domain of absolute value function is all the real number, which is R. And range is from 0 to positive infinity. So from 0 to positive infinity. This is the range, the y values that absolute value function can have. Look, we have no negative part. Okay? Or another reason we can say that, we always say that absolute value of any number is equal to a positive result. Positive. We never say that it's negative. Right? Remember, if it is equal to a negative, there was no solution. So since there is no negative, it starts from 0 up to positive infinity. That is regarding to the domain and range of an absolute value. So there is a question here. It says, draw the graph of y equal to absolute value of x plus 1, then find its domain and range. So this is the way that's actually called point plotting way to graph a function. We will take some point, then we will find their outputs, and then we will plot it on a coordinate plane. So our function is y equal to absolute value of x, y equal to absolute value of x plus 1. Inside the absolute value, again, it's x. So x equals to 0. 2 points less, 2 points smaller, 2 points bigger. So again, negative 1, negative 2, 1, and 1. So if we put 0 inside this, absolute value of 0, it's 0. But plus 1, it's equal to 1. Absolute value of 1, it's 1. Plus 1, it's 2. Absolute value of 2, it's 2. Plus 1, it's 3. Okay? Now, absolute value of negative 1, absolute value of negative 1 plus 1. Absolute value of negative 1, it's 1. Again, plus 1, it's 2. The same thing that we got from the right side. Absolute value of negative 2, absolute value of negative 2, it's 2. Plus 1, again 3. So let's plot these points. Let me just write them as order pairs. So negative 2 and 3. Negative 1 and 2, 0 and 1, 1 and 2, 2 and 3. Perfect. Imagine this is our coordinate plane. Our coordinate plane is something like this. So let's just plot them. 0 and 1. Here is 0 and here is 1. So let's say here is 1. This is our first point. Next one, negative 1 and 2. Let's say here is negative 1 and 2 would be somewhere like here. So here is going to be the point. Then we have got negative 2 and 3. Let's say negative 2 is here and 3 would be somewhere like here. So here is going to be the next point. Okay, 1, 2, and 3. Perfect. From the other side we have 1 and 2. So 1 here and 2 again is somewhere around that place. And how about 2 and 3? So 2, let's imagine it's 2 and 3 again is over there. So let's just connect them. So this is going to be our graph. This is how we are going to graph an absolute value function. So right now let's analyze the domain. Domain for absolute value function is always all the real number. Guys, from negative infinity it goes up to positive infinity. There is no discontinuity point here. Okay, that's why domain of absolute value function is all the real numbers, which is all the real numbers that are donated by R. How about the range? Range may problem. You need to be careful about the range. The lowest point is what? This time it's not 0. Be careful. The lowest point is on y-axis. Look, this is the y-axis, by the way. This is the y-axis. On y-axis, the lowest point is what? 1. So it starts from 1 and it goes to positive infinity. Positive infinity. So that is the range. Always from the lowest point to the greatest point. So the lowest point is 1 and the greatest point, look, it continuously just goes up. That's why it's from 1 to positive infinity. Perfect. So here the next one is y equal to negative absolute value of x, negative absolute value of x plus 2. Be careful about this one. Again, y equal to negative absolute value of x plus 2. Inside our absolute value we have got x. So equalize it to 0. It's 0. 2 points smaller, 2 points bigger. Again, it's not necessary to choose this kind of point. You may just choose 2 other points. But since these are easy to deal with them, why not choosing the easiest one? Alright. So let's put 0. Absolute value of 0, it's 0. Negative 0, 0. Plus 2, it's going to give us 2. Be careful. Absolute value of negative 1, it's 1. There is a negative out, so it's going to be negative 1. Plus 2, negative 1 plus 2, 1. Again, absolute value of negative 2, it's 2. But since there is a negative behind, so still the result is going to be negative 2. Negative 2 plus 2, 0. For the other side, we are going to reach the same thing. Like if you put 1, so you are going to get 1. If you put 2, you are going to get 0. So let's write them as ordered pairs. I hope, guys, that you can see what I'm doing. And you can just solve it by yourself at home too again. So the points are going to be negative 2 and 0. Negative 1 and 1. 0 and 2. 1 and 1. And 2 and 0. These are the points that we have. Our coordinate plane would be something like this. Okay. So let's just plot them. Negative 2 and 0. Here is negative 1, negative 2, negative 2, 0. So on x-axis, negative 2 units goes left. 0 means no movement on y-axis. So it's going to stay here. How about negative 1 and 1? So negative 1 is here. 1, let's say, is over here. How about 0 and 2? 0 and 2. Exactly here. This is 1, this is 2. 1 and 1. 1 is here and 1 is here. So here. 2 and 0. 2 and 0. Exactly here. So let's plot, let's connect, let's join this. Oops. I was about to clean it. Erase it. So let's just join these points. It may not be that much accurate, but this is going to be the graph. So it's open down, by the way, because of that negative. In transformation part, we will study it. Okay? So, this is how are we going to graph this type of functions. So right now, domain is, without thinking about it, domain is always R. From negative infinity to positive infinity. It can continue. And from the other side as well. So on x-axis, we can have all the values of real numbers. That's why domain is all the real number. How about range? How about range? So for the range, we said that the lowest point, or the lowest point this time is not that point. The lowest point, we will choose it from here. Since it goes down boundlessly, so we are going to say that the lowest point is negative infinity. Up to, it goes up until this point, which is 2. This time from negative infinity to positive 2. That is how you are going to find out the range of an absolute value function and graph it. And my dear students, I hope that you got benefit from this lesson regarding to absolute value. Still, there are something that we call them geometric transformation of absolute value functions. Well, actually, here it doesn't give it to us. Maybe it's because of the color. So I'm going to write it by myself. Y equal to absolute value of x. Look, horizontally shifted by a unit to the right. So x minus a. Y equal to, let me just completely write this one. X plus a. Vertical by units upward, absolute value of x plus a, y equal to of absolute value of x minus a, y equal to negative absolute value of x. These are the geometric transformation of absolute value function that we can have, that we have it actually in our book. And again, you will study it in grade 12 if the book didn't change, because this is exactly came from the grade 12 book. So horizontally shifted by units, by a unit to the right. These are the transformation regarding to the parent function of an absolute value function. If we have absolute value of x minus a number, okay? If there was minus inside, so we are going to say that our function will be shifted to right for a unit. For example, if we have y equal to, let's just give one example, absolute value of x minus 2. We will say that we will shift the parent function 2 units to right. Okay, right now we have examples. If we didn't, I'm going to make example for you, don't worry about it. And for how about this one, y equal to absolute value of x plus 2. If there was minus, we will shift it to right. If there was plus, we will shift it to left. How many units? According to the number of a. If it is 2, so 2 units to right. If it is positive 2, 2 units to left. So how about if the changing number was outside of the absolute value? For example, if y equal to absolute value of x plus 2. If it was adding to a number, you should shift it vertically up. Vertically shifted by a unit upward. So we will go up. How many units? It depends on the number of a. How about vertically shift by a units downward? So for example, y equal to absolute value of x minus 2. Okay? If the negative number, if it was subtracted minus by a number, so you are going to go downward. And in case if we have y equal to negative absolute value of x, if there was a negative behind the absolute value of x, you are going to reflect it across the x-axis, just like the previous example. Go back to the previous example. It was y equal to negative absolute value of x, I guess plus 2, if I'm not mistaken, or minus 2, plus 2 actually. So since there was a negative behind that absolute value, the graph was in this way. It was reflected across the x-axis. It was like open down. Perfect. That is regarding to the geometric transformation of absolute value function. Right now, let's just make some questions regarding to it. Let's see if we don't have it. So I'm going to make it by myself. We do have it, hopefully. So let's just draw them. Draw the graph of the following function by geometric transformation that we already studied using the parent function y. Where is my pen? Using the parent function. So parent graph means y equal to absolute value of x. So the first one, absolute value of x plus 2. What kind of shift do we have? What kind of movement do we have? If the number was inside the absolute value, we have horizontal shift. If the number was out of the absolute value, we have got vertical shift. Either go upward or downward. I'm going to repeat it. If the number was inside the absolute value, we are going to change horizontally, either left or to right. If the number was out of the absolute value, we are going to move vertically, either upward or downward. And if there was a negative behind the absolute value as a coefficient, we are going to reflect it with respect to the x-axis. So, the first one, absolute value of x plus 2. The number is inside. What kind of shift do we have? Excellent, horizontal one. So, how many units and to which side, left or right? We said if there is positive, we will go to left. Okay? If there is positive, we will go to left. So, let's just draw the parent function and the movement, the shift. Okay, the parent function is this one. This is the parent function, which is f of x equals to absolute value of x. But the movement, we said that we will move to left, how many units? 2 units. So if here is negative 1 and here is negative 2, so our function would come to here. This is how you are going to transform. From 0, it came to the left side for 2 units. If there was a number added to x, we need to move to left. If there was a number, let's say if we have y equal to absolute value of x minus 5, let's say. Okay, so for that case, since we have negative here, x subtracted by 5, so let's say since we have negative, simply we will go to right. How many units? 5 units. So let's say 1, 2, 3, 4, and 5. So the parent function would come to here. That is the function of y equal to absolute value of x minus 5. Okay? And here is, of course, y equal to absolute value of x plus 2. I hope that it is clear. It's easy. Try to understand it. Okay? Try to focus, repeat it, repeat the explanation, and see what we are doing right now. So try like different examples by yourself. Try to change these numbers. 2, make it 3, make it 4. Okay? And then the next example. Let me just erase it. Okay, make one more coordinate plane for the next example. Okay, so we have got absolute value of x minus 3. Since the number is out of the absolute value function, we are going to change vertically. We will shift vertically, either upward or downward. If the number was positive plus a number, we will go up. If there was negative, we will go down. So absolute value of x, this is the parent function, y equal to absolute value of x. It says that absolute value of x minus 3. So we have to go down for how many units? Perfect, 3 units, negative 2 and negative 3. So our function, our new function after the transformation would come to here. Okay, so the red one is going to be y equal to absolute value of x minus 3. Imagine if we have y equal to absolute value of x plus 1. How are we going to find this one? So imagine here is 1. Since 1 is outside, we will change, we will like move vertically. Is it positive? Yes, so go up. For how many units? One number, 1 unit. So the number, the new function, this is going to be y equal to absolute value of x plus 1. So this is how we are going to deal with transformation of a function that it is absolute value. Okay, with absolute value. And finally, the next one, when we have a negative behind the absolute value, we are going to reflect it with respect to x-axis. What do you mean, Mr. by this? Okay, let's just clarify it. Imagine if you have the parent function. That is the parent function of absolute value of x. F of x equals to absolute value of x. That is the graph of absolute value of x. How are we going to reflect it? If we have a negative behind the absolute value, we are going to reflect it with respect to x-axis. So, which means it's going to be in that way. It's just like mirror between them, the x-axis. So it's reflected with respect to x-axis. Okay. Imagine if we have y equal to negative absolute value of x plus 5. So how many chains do we have here? Well, we have reflections and vertical shift. Okay, first of all, the parent function is over there. Okay, so we are going to reflect it. We did it. And then plus 5. So we need to go up for 5 units. So let's say 1, 2, 3, 4, and 5 is here. So our function would be in that way. That one is the graph of y equal to negative absolute value of x plus 5. We reflect it, it's up and down, and we just move upward for 5 units. This is how you are going to transform an absolute value function. Guys, absolute value matter is easy. Like there are like the thing that we talked about it in this video was, let's say, first it was evaluating the numerical problems regarding to absolute value. Then we clarify like how many solutions are we going to have for an equations of absolute value. There were 3 cases. Then we came up with a graphing of absolute value. And then we discuss about domain and range and parent function, of course, how to graph it with like the method of point plotting. And then we finally studied like how to transform. We studied geometric transformations like horizontally, vertically, and of course the reflection type. So this is the end. But there are something else that it is in your book, like the characteristic of absolute value functions. I hope that you can go and check it. Characteristic of absolute value function, for example, absolute value of one of them was absolute value of a. B is the same with absolute value of a times absolute value of b. These are the characteristic of absolute value function. And absolute value of a is always greater than 0. It's positive. So these are the characteristics, and we have got more, by the way. For example, absolute value of a over b is the same with absolute value of a over absolute value of b when b cannot be 0. So we have got such a kind of characteristics for the absolute value. If you have got the books, go, I think if I'm not mistaken, it's in page 28. So 27 or 28 of the new book, go and check it. And try to know them, okay? But this is at the end of the video, the end of the 3rd lesson of the new book. I hope, just like always, you got benefit from the videos, from the explanation of me and my videos, and I hope that we see each other in another video. Take care of yourself and study perfectly. Thank you for listening to me.